This video lecture will discuss atmospheric pressure, including the motions of the atmosphere at high and low pressure zones. The Earth's atmosphere is composed of gas particles, and these particles have mass, which means that the force of gravity acts on them, pulling them down towards the surface of the Earth. So the density of the atmosphere decreases with elevation for two reasons. One, the farther up you go, the less atmosphere that you have weighing down on you. And two, the farther up you go, the weaker the gravitational attraction between the atmosphere and the Earth. This results in the atmosphere being much denser down near the surface of the Earth than up at higher altitudes. And to a person standing at the surface of the Earth, all of this pressure, the weight of the entire atmosphere is going to be exerting a pressure downwards, right? And so you have this atmospheric pressure pushing on you down at the surface of the Earth. However, that pressure isn't going to be the same all over the Earth, and it's not even going to be the same from one day to another. So to begin to understand exactly how it is that air moves through the atmosphere, let's begin by considering an analogy. Here we have a snapshot of someone laying right on the ground, and then their friend comes up and is about to pounce on them, right? Question for you is, how much pressure is the person laying on the ground about to feel? The answer is a lot of pressure, right? In our weather analogy, this would be considered a high pressure situation, except in the case of weather, instead of the weight of a person landing, we would consider the weight of an air mass descending, right? So high pressure systems are systems with downward or falling air. We need to be able to sketch what this looks like in both side view and top view. We'll start with the side view. How would you go about sketching some downward moving air? We could just use some arrows to indicate downward motion. But now we need to consider the top of the sketch. Where does the downward moving air come from? Well, it has to come from the surroundings. Those are arrows. Okay, so now, what about air at the bottom? What happens when our downward moving air hits the surface of the Earth? Well, it's going to spread out. Air is basically a fluid, and it's going to do the exact same thing as if you took a glass of water and you dump that water over and it goes down and then it splashes outward. That's the exact same thing that's going to happen at a high pressure zone. So, if high pressure systems are characterized by downward moving falling air, what do you think characterizes the low pressure systems? If you guessed rising air moving upwards, great job. At this point, go ahead and pause the video and see if you can make your own sketch for upward moving air. Okay, so this is how I draw a side view sketch of a low pressure system. So in a low pressure system, we're going to have air rising, but it has to come from somewhere. So if this is the ground, my low pressure system is going to look like this. It's going to come in, go up, and out, right? So we can see our rising air is coming from somewhere on the bottom, rising upwards, and then it sort of diverges up at the top. Okay, now we need to think about how both of these systems would look in top view, as if seen from a satellite. Starting with the low pressure system. So low pressure, rising air. Let's go ahead and just redraw that sketch. We have some rising air. Okay, now for our top view, we really want to figure out what's happening with the surface winds. So we want to zoom in on this part. And we can see that those winds are converging, right? They're going together before they go up. And so we know that we're going to have to draw wind that's going, air parcels that's going in towards a low pressure system. So if this is the low, then the atmosphere is going to be going towards. But we also know that because of the Coriolis effect, those airs are going to be forced to curve, and they curve to the right in the northern hemisphere. And so to the right, to the right, to the right, to the right. And so that is what we see for a top view low pressure system. Now for a high pressure system, we would have falling air like so, and the high pressure system is here on the ground. That's the side view. In top view, high pressure system has to be moving away. We can see that at the bottom here. It's moving away from the high pressure and curving to the right. So that looks like so. And that's how you would draw your side views and top views for both the high and low pressure systems in the northern hemisphere. Now the low pressure system, and I'll go ahead and redraw it, right? So low pressures, that's rising air, so it's moving in towards the low pressure zone. So it looks like this. And this ought to look like something you might have seen before. Hurricanes. Hurricanes are an example of what can happen when very low pressure systems form out over the ocean. High pressure systems, on the other hand, result in clear skies and sunny days. So let's think about why that is, why the rising air results in storms and the sinking air results in clear skies. We remembered that low pressure systems are rising air, so let's consider what actually happens to a parcel of air as it rises up through the atmosphere. Well, if we start by considering a small parcel of air down near the surface, and then we let it rise upwards, it's actually moving into a place with less pressure acting on it and smooshing it, right? And so when it moves up there into the less dense atmosphere, it's actually going to expand, right? Its volume physically it gets bigger. And when the air expands, there's going to be less collisions of all of the little gas molecules within it. And in fact, the heat energy of that entire parcel of air is going to be more spread out. And what does that mean? It means that the parcel of air is actually going to be forced to get colder simply because it expands. So, as we can see here, as air rises into lower and lower pressures, as it gets farther and farther up, it expands, it gets bigger, and that forces it to get colder and colder at the same time. Now we call this type of cooling adiabatic. Adiabatic just means that there's no energy input to the system and there's no energy lost from the system. Instead, all of the cooling is due to a change in volume of that air parcel. Now we have to remember that the air parcel we're talking about, it actually has water vapor in it. And what happens to the ability of air to hold water vapor as temperature decreases? Well, the ability of the air to hold onto that water vapor also decreases as the temperature does. So the colder our air parcel becomes, the greater and greater its relative humidity, until eventually it's 100% relative humidity. That is when the air parcel is saturated with water vapor. We call the temperature at which this happens the dew point temperature. In the example shown, the air parcel has a dew point temperature of 65 degrees, meaning that if you cooled that air down to 65 degrees, the parcel would be saturated and condensation, or dew, would appear. What does this mean for our model atmosphere? Well, as soon as an air parcel cools down to that dew point, so it's getting colder and colder and colder, and then it hits the dew point, and as soon as that happens, the air is saturated, and so condensation occurs. Physically, that means that the water vapor that used to be dissolved in the air parcel, some of it condenses out into liquid form, creating teeny tiny droplets of liquid water that we know as clouds. Of course, the opposite is true as well. If rising air is forced to expand, which forces it to cool down, sometimes all the way to the dew point temperature, then sinking air is actually going to contract and heat up, meaning that a sinking air parcel is capable of holding within it greater and greater amounts of water vapor. So sinking air actually has no mechanism to create cloud formation. This is why high pressure systems, falling air, are associated with clear skies and sunny days, while low pressure systems, rising air, are associated with clouds and rain and storms. All right, time to quiz ourselves. Which of the following images represents adiabatic cooling? If you selected C, great job. Adiabatic cooling means that you're going to have cooling occur simply as due to an increase in volume. So, which of the images represents adiabatic heating? Hopefully, you selected B. In this case, the number of molecules stays the same, but the volume that they are taking up decreases, forcing them to be tighter and tighter compacted, which is going to increase the temperature of our parcel there. So you might wonder how high and low pressure systems develop in the first place. Well, it has to do with the uneven heating of the Earth. Locations that receive a lot of heat energy or that are able to heat rapidly will be warmer than their surrounding areas. And what does warm air do? It rises. So in the image here, it's early summertime and the land surface is much warmer than the ocean. So the land surface heats the atmosphere directly above it, and if that atmosphere heats up to be warmer than the surrounding air, it will rise upwards. But what happens to rising air? It expands, forcing it to cool down adiabatically. Again, the term adiabatic just means no heat is gained or lost by the system. All the temperature change is the result of a volume change. All right, so this rising, expanding, cooling air is getting closer and closer to its dew point temperature. When it finally reaches that temperature, it is at 100% relative humidity. It is saturated. And so clouds happen, right? Because condensation occurs and this creates clouds, right? The clouds are made up of these tiny liquid droplets of water floating around inside of the atmosphere. These droplets collide with one another, growing larger and larger until eventually they grow too massive, too heavy to stay floating up there, and instead they fall back down to the surface as rain. Our atmospheric parcel is then less humid, right? It's gotten rid of a lot of its water vapor and it's floating out over C here, and it's going to sink back down towards the Earth. Now, as it sinks down, its temperature will warm up, right? But its temperature can't rival the warm temperatures over here on the land, because what's happening is that up high in the atmosphere, it's at maybe -40 degrees Celsius, possibly even colder. So heating up from that, by the time it gets down here, it'll be warmer than it was in the upper atmosphere when it's down at the bottom, but it won't necessarily be warmer than the surrounding areas. Now, once it is down here, you've got really dry air over liquid water, so it's actually going to evaporate some of that water and then blow onto land. And then you have wet air parcel heating up due to the heat on the land surface again, so that if it rises again, it will still have moisture and be able to lead to storms onshore. So, can you place all of these terms here in their appropriate locations on the image? Go ahead and pause the video. Hopefully, this is what you have. The warm land surface provides heat to the atmosphere above. Hot air rises in a low pressure zone. This is going to, of course, lead to volume expansion and cooling down, and then condensation, and then rain, right? Over here on the other side, we have cold air sinking downwards. Downward falling air is high pressure zone, and the ocean over here is much colder than the land surface, or else none of this circulation would have initiated. Okay, one more thing to recognize is that the entire effect is seasonal. In the fall, the land doesn't receive as much sun as before, but at this point, the ocean water has been storing up heat energy all summer long. So the ocean is going to slowly release this heat back up into the atmosphere, right above it. And that is going to cause the atmosphere there to rise. Now, do you think that you can place the terms in their appropriate locations in the image? Go ahead, pause the video and give it a try. This concludes the high and low pressure system video lecture. At this point, you ought to be able to sketch both high and low pressure systems in both side view and top view. You also ought to be able to explain why one is associated with storms and the other with clear skies.